Hi, everyone, and welcome to this month's MAPP webinar. This is Dan Barry from NOAA, Climate Program Office. The topic of the webinar this month is drought prediction, and we are going to hear from 4 speakers, Eric Wood from Princeton University, Brad Lyon from the International Research Institute for Climate and Society, Siegfried Schubert from the NASA Goddard Space Flight Center, and Kinsey Mo from the NOAA Climate Prediction Center. One of the things I'd like to tell you about before we get started is that we've organized, as a program, we've organized a task force on the topic of drought. And the task force is composed of individuals who are funded on projects by the MAPP program working on drought prediction as well as monitoring and understanding. Last month's MAPP webinar was on the topic of drought understanding and monitoring, and this month we're going to hear about the prediction component. This task force is composed of about 30 investigators that this program funds, and they're drawn from academia, from federal agencies, especially NOAA, and also from federal laboratories and operational forecast centers. They're engaged in a number of activities. They have a monthly phone call, and they're preparing a special collection for the Journal of Hydrometeorology that's titled Advances in Drought Monitoring and Prediction, and there will be over 20 papers in this special collection once it's published, and the papers are each written by an investigator that participates in the task force. They also hosted an AGU 2012 fall meeting session titled Advancing Drought Monitoring and Prediction with Applications to Decision Making, and we held a task force meeting in Fort Collins, Colorado last year. They're also working on a special NIDIS report on the topic of the 2012 drought, which will include some attribution work, and that's being led by oh, sorry, the name's slipping my mind at the moment, actually, but I'll get that to you later. And the 2 of the speakers that we're going to hear from today, Siegfried and Kinsey, are co-leads of this task force, and Eric and Brad also participate in the task force. So, Eric, are you on the line?
I'm on the line.
Okay, great. So what I'm going to do is switch over control to your computer.
Let's see.
And then you want to click that Share My Desktop button.
Oh, do I have to, hold on.
No problem.
Share my desktop. So I clicked on that.
Great. Okay, so we can see your screen now, and then just go to your PDF slides, and
I'm opening it up as we talk.
Great.
Here we are. So
right.
I'm going to give a talk about some of the recent work that we've been doing. It's a bit of a buffet, a smorgasbord, and some of the challenges of what we're trying to do. We could spend a whole seminar on any of these and many others which we've been working on, but the 3 which I thought would be of interest today is work that we've been doing. The first one on land-atmosphere coupling and how that relates into drought predictability. We've observed in our own analysis of CFSV2 a summertime seasonal drought forecast breakdown, and we've been doing a lot of work on the coupling that is implied in the models. This grew out of work that was done where we use satellite data to understand coupling. You know, there's been a lot of work in the literature through the Glassé experiments on that, and there's a couple of papers. One coming out in the Climate Dynamics CFS special issue, which is this one, the bottom one, is about to be submitted. Then I want to talk a little bit about hydrologic predictability and what are the limits and the impact of initial soil moisture conditions versus precipitation forecast skill and some of the work in that. And then finally, I want to talk about determining probability of drought recovery in a statistical, robust way, and I'm going to show some results for this year, which are pretty sobering results. So most of it's going to be talked on the first one, Josh Roundy is a PhD student who is building on work that Craig Ferguson did based on satellite data on looking at coupling, and this was in response to the Glass A's, where they have all sorts of coupling results from different models and no sense of how you can do it at regional and global scales through observations per se. And so the questions that we're really concerned with on the top here is the temporal variability of land-atmosphere interactions and how does it play into these extremes of drought and wet conditions. And so Josh, in fact, has developed, we've looked at what we call dry coupling days and wet coupling days. And what he has done is he's taken convective triggering potential and humidity index, which is a standard way. Kirsten Findell, when she was a PhD student up at MIT with Fatih El-Tahir, developed a framework where they use some radiosonde data. So in this diagram here, this has been generalized, and this is results for the southeast. Their two little red boxes are what Kirsten did, and in fact, if you analyze these spaces and look at precipitation, you actually get a much broader range of the humidity index and the convective triggering potential. The interesting thing is the persistence. So in the bottom, you can see the frequency. Mostly it's wet coupling, but there's dry coupling, and the persistence lasts a long time. And so on the right-hand side, you see an example. This is from 98, June through July of 98, and the bottom one is in 94, again, June, July, dry coupling, wet coupling, and you can see the same color bars, so wet coupling and the dry coupling, the blue in the top is the soil moisture, and the red is the convective triggering potential, and the green is humidity index. And you can see the rainfall. You can see it rains during dry coupling, but the amount of rain is significantly less. And that has led us to think about how well do the models do. And so what you see here is that CFS-V2 fails to hold dry coupling. And when you look at this coupling drought index, relative to what you see in the CFS reanalysis. And so in the top, now, here's the problem. The problem is the resolution of the reforecasts and the resolution of CFSR in the atmosphere are different. And so we have created a low-resolution CF reanalysis to be equivalent to the reforecast. Nonetheless, what you see in the top diagram is the reanalysis in red of the coupling drought index and the precipitation bias relative to the NLDAS. And what you see is that as soon as you initiate a forecast, you get CFS falling off and becoming into a wet bias. And this is over 28 years, and I think this one is for either for the Southeast. We've also done it for the Great Plains. And if you look in the bottom table, the Great Plains, the reanalysis, and the CFS forecasts have different climatologies. And it is a big problem because you initiate things with CFSR, and then it completely falls off the table. And part of that, I understand, is due to changes to be made, according to Mike Egg, to reduce a warm bias. So they're sucking water in the forecast model out of the lower soil layer, even though the other day Hoog said that CFS-V2 has a wet bias. So I mean, there's issues here on parameterizations, but the biggest concern that we've been looking at is this collapse of holding the drought index from dry coupling, and that's something that we're actively developing, and this figure is in that paper that's about to be submitted. I can get to go to the next page. My poor computer doesn't want to change pages here. Come on.
It's okay, we can wait for a little bit.
Oh, I don't know what's happening here. It doesn't want to go to the next page here.
We'll wait it out a few more. Oh, there we go.
Okay. Hold on. This?
Yeah.
Here. So here is the comparisons between CFS-R and the reforecast showing a divergence, especially the ones I've circled. Drought index, precipitation, so the precipitation, this is forecast minus reanalysis, initialized, all years initialized end of May, June through September forecast. And you see it's too wet. The reds are high values in the anomalies. You have the CDI is low, which means wet, it's preponderance of wet coupling. Too much cloudiness, you can see the short wave is bad. Too much evaporation. So there's some land surface parameterizations and atmosphere coupling that needs to be done. And in fact, what's the challenge to fix it? It's hard to know. How does the coupling in the forecast differ from reanalysis and in the reforecast? And so we're in the midst of doing some attribution in this. Part of it might be this drawing water from the lower layers. It might have to do with other things. And we have a few hints that we're moving at, but I'm not really quite ready to do that. But it is a very, I think that this, and we've been trying to get full resolution data and get data for 2011 and 2012. And people at NOAA know that we've been working with Mike Eck to try and do this, and we've been unsuccessful. And those are 2 case studies that we want to spend time on. So if that happens, we'll be happy people if we can get that full resolution data. We can't even get the reforecast data there. The second thing, so that's our work in looking at coupling and how coupling the failings in coupling may result in failing of holding drought in these forecast models. I'll just hint and say one of the things we're looking at as it fails is sources of local moisture and moisture from a longer distance and trying to understand that. And again, we need better resolution atmospheric data from the reforecast, and we would like to have the full resolution for these 2 years as case studies, but we haven't been able to secure that data yet. Sources of hydrologic predictability, are there limits? And there's a couple of papers that we've been looking at between initial soil moisture versus precipitation skill. And this is an area where other people, the first paper by Shukla is a student of Dennis Lettmeyer's. We've been doing this with this. It's using extended stream flow prediction and reverse stream flow prediction. We've also been interacting with Albert Van Dyke in Australia, who's been looking at seasonal stream flow predictability using over 6,000 small catchments worldwide. This figure gives the initial soil moisture and snow conditions. It shows that it dominates in hydrologic skill over the quality of the precipitation forecast as a source of predictability. So in the 1 month lead, which is the column on the left, and the rows are, the first row is forecast period January to June, and then April to September, then July to December, and October to March. The first column, 1 month lead, and then there's 3 month lead and 6 months lead. It goes from red to blue. And as it goes from red to blue, you lose the initial soil moisture. That is, knowledge about the initial soil moisture gets lost, and the precipitation skill dominates the skill of the forecast. So this basically says that it is critical that, and you can see over North America, it's a big issue for most of the forecast periods, except for in the wintertime. It's critical to have quality initial soil moisture so that we can make quality hydrologic forecasts, so whether it's soil moisture, drought, stream flow, what have you. In this slide, where these are from the paper of Albert Van Dyke was the lead, they ask, what's the extent the climate anomalies provide information useful to seasonal hydrologic prediction? Climate anomalies being ENSO and PDO and these things. And apparently the answer is very little. He looked at these 26 indices over long periods of time, and the bottom slide says, what's the contribution of the climate indices to the theoretical skill? And he has a measure looking at the mean rank correlation with this. But the bottom line is that we struggle with trying to see consistently over long data sets that climate indices add much. And I know there's a discussion in the last Drought Task Force telecon where they looked at 2012, and there's absolutely no indication that tropical SSTs played any role in last summer's drought over the central U.S. And the question is, years where they do, is that just a randomness, or is it actually, is there something different going on? So I think this is a real challenge to really understand. Maybe we're drilling down the wrong spot. So that's and what I have not shown you, but what we've done work on. The coupling, the strength of SSTs to precipitation is much stronger in models. That is, the correlation is much stronger in models than it is in observations. The models indicate that contribution to things like ENSO should be much higher than you actually see it when you go look at the observations. And the answer is, the question begs is, why is that the situation? The last bit of work that we've done is probability of drought recovery and what's the right way to go do it. A lot of times there's procedures where they just say, well, if we have 6 inches of water, we'll all be fine. It turns out that doesn't quite give you the right answer. What we've done recently is that we integrate our drought monitoring and the seasonal hydrologic forecasting to do this. 15-minute notice. Well, we'll be out of here. We have 2 quick slides, Dan, and I'll be out of here.
Okay, thanks, Eric.
We did an ESP 50 years starting on our end of February drought monitor. Each of those dots, so the plots here shows cumulative precipitation ranked from the highest to the lowest over these different leads out to 5.5 months, 6-month leads. Each of the dots is a different year historically, starting from the same initial condition. So if you go out to 4.5 months, we did that, then we fit a copula. We use copula statistics to go fit this. And so you can see for this point in Iowa, what is the chances that you're going to be above the 40th percentile of our drought index? And it's not very big. You know, it's just that little area. The red line should have been shoved over, and I didn't do it, so it's around the 40th percentile. And the next slide shows you what it is for a 4-degree centered area, and that's closer to the 50th. The answer is pretty low. So it appears that it's going to be a real challenge, but I think running long-term ESSP and fitting joint distributions, you can do risk analysis looking at the what's the chances of recovery and over different time periods. And you could even do total forecasts of rainfall and then do subsampling as if it's from, take the ESP ones and put it through there, because timing makes a big difference. And it shows, this is some maps that show what it looks like across the United States. We're generalizing this in a historical context, and we're working on that right now, and we'll do that. But, you know, there's parts of the country that are going to be dry this spring, regardless of how much rain comes out. And if I can get it to respond, we'll get the last one, which is the conclusions. But maybe I'll just...
Like that actually might be the 13th out of 13 slides.
Conclusions. People can ask questions.
Okay, great. Thanks so much, Eric. So I'm going to unmute everyone on the phone. Before I do that, can you please check your mute buttons and make sure that if you're not asking a question that your phone is muted? Okay, so does anybody on the phone have a question for Eric? Any questions for Eric? Okay, Eric, well, thanks a lot for the presentation.
Thank you.
Our next presenter is Brad Lyon. Brad, are you on the line?
Yes. Can you hear me okay?
Yeah. Sounds good. It sounds like there might be an echo. I'm not sure. I don't know. We'll give it a try. So I'm going to change presenter privileges over to your computer. And what you want to do is click the Quick Start tab and then click Share My Desktop.
Okay.
Brad, are you there?
Yeah.
Okay. Do you see that? There you go. Okay.
Right.
And then can you bring your slides up? Great. And then just go full screen, and whenever you're ready, go ahead.
Okay. Yeah, thank you. And my apologies to Eric and others. I had some difficulties, so technical difficulties, so I wasn't able to catch the first 2/3 of the first talk. But what I'm going to talk about briefly is just some of the work that's actually an outgrowth of an earlier climate testbed project with Arun Kumar and Marty Hurling. And basically the idea here was to look at just meteorological drought, looking at basically precipitation variability and how it affects various drought indicators. Primarily what I'm going to talk about today is this standardized precipitation index. I've got Anthony Barnson here and Kingsley listed because they're part of a sort of an extension of that work where we're looking at the NMME, and Kingsley's done some nice work in terms of the meteorological drought indicators using the NMME as part of that. So basically, in this approach, we're saying we want to merge in terms of making predictions of meteorological drought indicators, observations of precipitation with forecast precipitation to come up with ultimately forecasts of things like the standardized precipitation index. So when you do that, of course, you have some built-in persistence in the indicator itself, and that's going to be a source of skill, so you need to back that out when you look at the actual dynamical model forecast of precipitation to see, you know, is it adding anything above the baseline. But in addition, you can use the baseline in those seasons and locations where the models don't have any skill. So if I can get this to advance, basically my quick talk here today will be about looking at these these baseline probabilities, and then looking at, in terms of dynamical models, the CFS V2 in predictions of the 6-month standardized precipitation index to see where we can get skill in what seasons above the baseline. But we're going to do that sort of in a hierarchical fashion. So first, this was work that was sort of headed up by Marty Hurling and Xiaowei Quan at ESRL, is to say, well, what benefit do we get, say, just looking at SSTs? So we're going to look at the atmospheric component of the GFS, and then look at what do we get from the fully coupled model, which would include the initialized land surface condition and atmospheric condition. And then just very briefly about how we can try and tease out more skill from the NME through some model output statistics. So without getting into too much detail here, basically here's the idea in the next slide, looking at this case where we have no seasonality in precipitation, say, and we're looking at these different standardized precipitation indicators. So the numbers just represent the different accumulation periods, so 3 months, 6 months, and so forth. So we set this up to see what's sort of the inherent sort of timescales associated with the variability of these indicators. And so we created some synthetic time series that by design have no month-to-month autocorrelation. They're not serially correlated, just to see what the persistence characteristics are. And as people have shown in the time series analysis sort of literature, if you do that and you basically put a running process through random numbers, you get this sort of behavior. So here's the autocorrelation at different lags. So obviously at 0 lag, you're starting at 1. And if you increase the lag, you see that all of these indicators have a linear decrease in the autocorrelation with lag time. And it drops off as basically 1 over n, where n is the accumulation period. In other words, if you have a 3-month SPI, after 1 month, you drop off the autocorrelation to 2/3. Okay, after 2 months, it drops to 1/3, and then you lose all the signal at 3 months, sort of thing. And it turns out there's nothing special about the SPI. You could do this with 3-month moving averages, percent of normal precipitation, anything you'd like. It drops off in that same behavior. And actually, in actual observations, say here in New York, where there's not much month-to-month autocorrelation and precipitation, the actual observations show this sort of behavior where you get this linear decrease. So again, our purposes in doing this is twofold. Number one, we need to back out this sort of level of skill being measured by a simple temporal correlation when we're including the model forecasts. But again, where the models don't have any significant skill in predicting precipitation, this gives us something that we don't have to just throw up our hands. We can say, for example, the longer the integration period, the more skill you're going to have. So, for example, an SPI 12 at 6 months by design is going to have a correlation of 0.5. It turns out that seasonality in precipitation modulates the autocorrelation behavior, and so we had to quantify that as well. And so this is just a quick map showing that. I've chosen, this is across the state of California, averaged across all grid points there for 2 different start times. So my 0 lead is in March on the left-hand column here, and then the right-hand column, my start time is in October. So basically the end, generally speaking, of the precipitation season on the left and the start of the precipitation season on the right. So say we go look at the SPI 6. We know that there's no seasonality in precipitation, that I'm going to get this sort of this linear decrease in the autocorrelation. But in this case, my autocorrelation, where I have this seasonality, is increased. Basically, you're reaching the end of the precipitation season. If you're in drought at the beginning of that dry season, obviously it's going to persist, is basically the intuitive result there. And the longer the accumulation period, the more dramatic the effect. But as you see, there's substantial skill here out to several months. I mean, you can get correlations in the SPI 12, above 0.9 at a 6-month lead, for example. At the other extreme is when you're entering into the precipitation season. So then you're, for example, in the case where you're in drought in this meteorological sense, at the beginning of the rainy season, you can quickly ameliorate that signal as precipitation season begins. So we need to quantify all these things ultimately to compare with the CFS forecast. Just quickly, another thing that we did was saying, even though this is just the baseline case, we could do better than just sort of this straightforward sort of standard persistence measure that I just mentioned. I won't go into the details here, but basically in this approach, say you're looking at the standardized precipitation index again, we want to look at the autocorrelation. We can show, depending on our approach, if we're a little more clever about it, that again, even for the case of no seasonality, where I showed previously, you're going to have a linear decrease. And our optimized method, you can actually improve the skill from what you would see here. So here's just the autocorrelation of our new approach, this what we're calling optimal, but only in the baseline sense. And this is for the case of no seasonality. In the case of seasonality, you can get an even more dramatic increase. But depending on whether you're entering the rainy season or at the end of it, the modulation by the seasonality itself can affect things quite dramatically. So ultimately, we use our optimized approach to give us the most baseline skill and to compare the models. So the models have to beat this baseline skill to be saying that they have any skill that's usefully adding to our prediction effort. One thing I didn't mention here is that on the left-hand side, there's a couple of things that, again, this isn't all that sophisticated, but there's some practical consequences of this, sort of our optimal persistence approach. Again, there are many cases where we know that precipitation forecasts are particularly challenging, particularly during the warm season. And in our optimal approach, there's a couple of things that, for example, if you look at the change in skill with lead time or lag, say you're looking at this middle plot, that here's my standard measure of persistence, the autocorrelation in the gray line, and then the black is our optimal method, that you can actually have an increase in skill with increasing lead time, if you will, basically because you're entering into the dry season. And a practical consequence of that, depending on the seasonality, is you can actually, rather than having your typical persistence, which is constrained, is going to decay, you can actually get some amplification of the signal. So here's a simple example from this flash drought that we had last year across the central part of the U.S. So here's two types of persistence forecasts for this SPI3, a 3-month standardized precipitation index. So this is a initial condition starting at the end of May in 2012 for the forecast for the end of July. So it turns out the end of May was, or the month of May was unusually dry. So in our optimal method, that tends to create drier conditions than our ordinary. I have the ESP here, but it's just sort of my standard measure of persistence. So this has some practical consequences in that, for example, if I look at this region here over Kansas, if I look at, say, the probability of my drought indicator being less than some selected value, could be minus 1.5, that climatologically everything's Gaussian, so that probability would be 6.6, just to distinguish between just climatologically what those probabilities would be, and sort of my standard measure of persistence would be, say, 9.5% or so. But in this optimal method, because it's capturing what's occurred most recently, there's a big hole to get out of here that you can actually show that the odds are substantially higher. Now, obviously, it's going to be the same for higher thresholds. So again, knowing nothing else from the models, this can be a useful bit of skill, rather than just saying throwing up our hands, the models aren't giving us any forecast skill. This just shows that, as we all know, the drought developed in the central part of the U.S. in 2012. So here's where we're looking at the source of the skill in the CFSV2 beyond the baseline. And so we're going to be predicting the SPI6 at one season 3 months ahead. So I'm starting with the GFS, the atmospheric component of the CFS model. So the idea is this, that this is my verifying season here, say DJF. So I'm using model precipitation forecast for DJF on a 6-month predictor that has 3 months of observations going into that, and then the forecast. So this is the same thing for March, April, May. This is the predicted part, and then there'll be 3 months of observations. So we see, just looking at the raw skill, that of course we get skill everywhere across the domain. But of course that's because I'm looking at a 3-month lead time, and I know there's inherent skill built into the SPI6. So after I subtract out the baseline, I get a map that looks like this. So it's quite challenging. We have something like 27 years of data to say, you know, you have a statistically significant difference between two correlations. So So what's plotted here in terms of the yellow says that the correlation skill is improved, but not significantly significant. It's not statistically significant. And the red shows where it actually is at 90% confidence, given our small sample size. That's the best we could do. So you see, for example, in DJF, the additional skill that you're getting kind of makes sense that it's somewhat ENSO-ish across the southern tier in particular. And you can see in other seasons, yeah, you're not gaining so much, maybe a little bit in the southwest in March, April, May. This here in the west coast doesn't tell us much, given that the season is June, July, August, and maybe a little something across the southern part of the U.S. and into September, October, November. So this is kind of what Eric was getting at, too, I guess, depending on the extent that the models may overdo things. In this case, this is compared to obviously the actual observation. So as we know, there's some ENSO signal there. If I look at the CFS, so in other words, this case, I would get the fully coupled model. So I have the sea surface information I'm getting from the model, plus I have the advantage of initialized land surface condition and atmospheric condition. Of course, my first set of maps here is based on a seasonal time scale, where on a seasonal time scale, the initial atmospheric condition doesn't buy you very much. And as people have shown looking at land surface, typically that signal decays on time scales less than a season. So DJF, there's some differences, but again, there's some sampling issues here. But generally, enhanced predictability across the southern tier relative to the baseline, maybe up here in the northern part of the U.S. And maybe a hint of some added benefit here in June, July, August in the plains, but nothing outstanding. So one thing we did is we said, well, how about on shorter time scales? Because we know, for example, the effect of the atmospheric condition and the land surface is typically going to decay faster than on a seasonal time scale. So if I just looked at 1 month forecasts and plug those 1 month forecasts into my SPI indicator here to get for a seasonal total, you're going to get additional skill. So particularly in the wintertime, this could be from atmospheric conditions. I think Siegfried is going to talk in this webinar a little bit about Rossby waves and, blocking type situations where you have, if you can latch on to some initial persistent feature, at least relative to synoptic time scales, but maybe not lasting as long as a season, you can get some additional skill. And so, again, when we're trying to tease out as much predictability as we can, maybe there's something we can say in the subseasonal time scale if we can't say something as confident about the full season. And you see this quite most dramatically in DJF, but you also see broader areas of the warm colors here in June, July, August, and into the transition seasons. So again, predictability on different time scales. What can we say in the subseasonal time scale in addition to looking at things on the seasonal time scale, particularly during this last event? Of course, we all tend to get fixated on the most recent event because it had this flash drought characteristic. Then the next drought will do some slow on variability, and then we're fascinated with that. But nonetheless, that is of interest. And then finally, just sort of a schematic here, trying to get at the idea of saying, well, we know there are obviously things like amplitude biases, and Eric showed in much more detail the different kinds of issues that there are with the models. But say just in terms of precipitation, we can try and deal with an amplitude bias in terms of the model being too wet or too dry relative to observations. But it's also possible that, and we've seen this at the RI and making seasonal predictions for different parts of the world, looking at different models, that they can have sort of systematic spatial biases. So the idea here is to say, well, if we can correct those through some type of model output statistics as through an application of canonical correlation analysis or something like that, maybe we can improve the skill. So this is just trying to get at one example of showing the kinds of thing that you could do. So at the top, Tony Barneston gave this to me, that for JFM precipitation correction using the CFSV2, and he uses one canonical mode, and if you average across the domain, you see here that the average correlation skill is quite modest. barely above 0 on average over the whole domain. And when you do this type of technique, of course, you have to be worried about overfitting the data. So there's some strict cross-validation. In this case, he left out 5 years in the cross-validation effort. So the gold colors indicating skill, blue no skill at all, and just the contrast between the two saying, well, there's more warmer colors in the bottom that, for this simple measure of aggregated across the domain, that the average anomaly correlation has jumped to 0.19 or something. The idea is, again, it's not a huge change, but again, we'll take predictability wherever we can get it from. Of course, looking at this map, we see the best skills enhanced here over the very drought-sensitive region of the northern Gulf of Mexico, which isn't particularly useful for most applications that we're thinking of. But nonetheless, if you do look over land areas, you can see that you can improve the skills. So that's the basic idea. So that's a very quick summary of some of the prediction things we're doing. And I think I'll leave it there. Thanks.
Great. Thanks so much, Brad, and also for the drought prediction-related humor. That was entertaining.
It's my dry sense of humor.
Oh, boy. Unintended. Thanks. So what I'm going to do is unmute the phones again. If you're not going to ask a question, please make sure your line is muted. But otherwise, on the phone line, please let me know. Are there any questions? Brad? Okay, well, Brad, thanks so much for your talk. If you have any, if anybody does have a question for Brad, please feel free to email him after the webinar. I do want to mention, at the beginning of the webinar, I mentioned that there's a NIDIS report that's being put together on the 2012 drought, and that's being prepared by Martin Hurley. I couldn't remember his name off the top of my head at the beginning of the webinar, but that should be released at some point this spring on the 2012 Central United States drought. So our next speaker is Siegfried Schubert, and Siegfried couldn't be here for the webinar today. He's on travel. So what I'm going to do is play a recording that we made of his talk from last week. So bear with me for a moment while I bring this up on the screen. Okay, so this is Siegfried Schubert's talk.
Okay, I'm going to be talking about drought prediction and in particular the role of and predictability of stationary Rossby waves. This is work I've been doing with my colleagues at Goddard, Yihui Chang, Harlan Wang, Randy Koster, and Max Suarez. So just as an overview, the idea is that there are a number of different controls on predictability and prediction scale, and at the longer time scale, it's of course SST, and intermediate time scales, it's the land, and at somewhat shorter time scales, so the monthly and weekly time scales, the atmosphere still plays some role. And that's what I'm going to be focusing on here. And if you go to slide 3, it sort of gives an overview of the different sources of predictability and where, at what time scale there's noise and at what time scale there's signal. And in particular, I've highlighted the planetary waves, which act as a signal at sort of monthly and shorter time scales, and of course they become the noise at the longer time scales. And so what I'm going to be talking about in particular is, first of all, looking at the basic structure of the leading waves, and then talk a little bit about their impact on precipitation and surface temperature. Then I'll be focusing on what forces the waves, and then I'll end with a look at the predictability of these waves and looking in particular at some case studies. So if you go to slide 5, then it's basically showing the overall structure of the waves. Here what I'm showing is lead-lag correlation, where you just pick a point over the Great Plains and then look at, this is now for data that's been filtered to contain the time scales of 10 to 30 days. And you can see that these waves have a structure that's sort of confined to the mean jet, And then if you look at over the course of a few weeks, you see that these time scales, things sort of propagating slowly to the east. If you go to the next slide, then we see the waves that have been filtered at some longer time scales, so now looking at 30 to 90 days. And again, now you see it sort of emphasizes the sort of the stationary component of these waves, and you see that the waves, again, they're confined to the mean jet, and that they're pretty much stationary. And you can, if you look closely, you can see sort of the energy sort of propagating through the waves over the course of a couple of weeks. So what we do next is to quantify the structure of these waves by just a simple EOF analysis, actually rotated EOF analysis. And you can see these very same structures that we just saw in the correlation fields. And the first mode, it turns out, is a wave that's very important over Eurasia, and we've been doing a lot of work there, and there are links to heat waves and droughts there. But what I'll be focusing on here is the second and third EOFs, which have an impact over North America. So we'll just look very briefly at the connection of these waves, upper level waves have to the surface. And so the next slide shows just the correlations of these waves with surface temperature and precipitation. If you just kind of focus on the right-hand side, it just gives you a sense of the what type of anomalies we can expect in surface temperature and precipitation associated with these waves. And the correlations are in places greater than 0.5. They're very significant, and we'll see in a minute that they actually look like that when we look at individual events. So what forces these waves? It turns out we've done a fair amount of analysis on this, and what the next slide shows is our ability to recover these waves if we force them. We force a stationary wave model with the different forcings, the transients, the diabatic heating, and so on. And it turns out what I'm pointing to there is that it's really the vorticity transients which seem to be the key forcing these waves. And we can actually put in some idealized forcings into the stationary wave model, particularly in the jet region in the Pacific, and you can see these waves developing in the course of a couple of weeks. So these clearly seem to be stationary Rossby waves. So now what we're going to do is focus on a couple of events, and so we're going to look at the next slide shows, again, the structure of these waves and then the time history of their amplitude. And you can see, for example, I've highlighted a couple of periods, June of 1998, when the second EOF has a strong large negative value, and then June of 88, where the third EOF has a large negative value. So those are the two events we're going to look at. The next slide, again, I show the structure of these waves, and then on the right, I show the actual wind anomalies during these two Junes. And the point here is clearly you see the structure of these waves are very clearly within the full anomalies themselves, so they're not sort of subtle things. They're actually dominating the wind field, upper level wind field during these events. And then the next slide just shows the correlation of these, again, the correlation of these waves with the surface temperature and precipitation. And on the left, I show the actual surface temperature and precipitation anomalies. It's a little bit hard to see, but the main point I want to make here is that if you look closely, the actual anomalies over North America very much resemble those correlations. So again, just to point out that these waves do have a very significant impact and contribute to the big anomalies that occurred. Of course, June of 1988 was a big drought year, and June in particular was sort of the height of that. And 1998 also had very significant dry conditions to the south and warm. So two very extreme years. And just looking now at the next slide, the evolution in time, we're looking at a Hobmiller diagram here. That's 40 to 60 north of, again, the upper level V wind, the 250 mile V wind. On the left is the daily data, on the right is just a filtered version of that. And the point is, you really see that early on you see a lot of sort of synoptic activity, and then starting at the late May and early June, you see these things kind of locking in, and these things remain stationary for on the order of a month or so. The next slide is the same thing, but for 1998. Very similar, and showing how these things lock in and remain stationary for about a month or more. So just a quick summary so far. We've identified these leading Rossby waves. They tend to be confined to the mean jet. Jet acts as a wave guide. They appear to play an important role at times in some of these extreme events. We've shown that they're primarily forced by submonthly transients. And so the question is, can we actually predict these, and do they help us stay on a monthly time scale? So now we're going to look at a few experiments where we look at these events, again, June of '88 and June of 1998. And we're also just recently added June of 2012, obviously because of this big interest in this sort of flash drought that occurred at that time. And what we do is to just get back up a little bit, May 20th, and we perturb the atmosphere and run 32 simulations, sort of hindcasts, with observed SST in all the cases, to just get some sense of how predictable these things are. So then the next slide sort of summarizes for all three cases the upper level wind evolution. This is now the ensemble mean of all 32 cases for each event. Again, on the left is the daily data, on the right is the filtered data, and clearly you see the model is trying to, is really producing these sort of stationary events early on, again, sort of a lot of activity, and then things become sort of stationary, and the ensemble mean signal extends out to through most of June, and depending on the case you look at here. But very clearly, the model is trying to produce these stationary events. With the caveat here is if you look closely, it's tending to retrograde the waves themselves, or they're actually propagating somewhat to the west, and I'll come back to that. That's probably a problem with the model. Then focusing on the 88 itself, again on the left is the upper level wind field, the V wind evolution, and then in the middle is the precipitation, showing these very dry conditions extending here in the ensemble mean out into at least the middle of June and perhaps a little further. The temperature, you see this signal extending much longer. This is in part coming from the SST response that's fairly strong during this time, and we see that extending much beyond June. But certainly in the first part of June, there appears to be a strong signal coming from the initial atmospheric conditions. So then the next slide is just showing now the shaded is the actual event in MERA. So looking again at the 250 millimeter V wind, and then the contours are the forecast. And what you see is very similar in terms of the amplitude and the length of the anomalies, but you clearly see the model tending to retrograde anomalies to the west, whereas in nature they're pretty stationary, and if anything they're kind of propagating slightly to the east. So that's one of the key problems we have with the model, and I'll say a little bit more of that in a minute. And finally, just a very complicated slide at the end is trying to look at all the ensemble members together, and here we actually do a complex EOF analysis that kind of provides you with the phase information as well. So we project all the anomalies onto this single EOF that you see on the left, where it's showing how things propagate the phase information that's on the upper left of those panels. And then on the right, this sort of spaghetti diagram shows the individual ensemble members, and the color scheme is such that it gives you the phase information, what sort of phase it is in at any one time. So the blue indicates a phase between minus 45 and 45, and so on. And the colored and circled line gives the actual anomalies from MERA. So a couple of just things, if you look at the colors themselves, you see that the model clearly has information, predictability quite far into June in the sense that all the ensemble members have the same colors. So you see it evolving in time from blue to red and back to blue. And the biggest event happening sort of early the first half of June. And MERA shows a similar behavior, but instead of going from blue to red, it goes from blue to gold. So it's tending to go slightly, as I said before, propagating to the east, whereas the model is retrograding things to the west. So clearly a predictable signal, but it's not consistent with nature in the sense that the models tend to retrograde things. And we believe that's a problem with our model of having too weak a Pacific jet. That's something we know is a problem with the model. So in summary, I think we've shown that these sort of Rossby waves play an important role on monthly timescales over parts of many regions of the Northern Hemisphere, and particularly over North America. At times they're the primary forcing of these extreme temperature and precipitation extremes. They appear to be predictable on sort of the monthly timescale and shorter, but on seasonal timescales they look to be fairly unpredictable. And we believe that's one of the big problems we have with our seasonal forecasts, that these things have large amplitude and they tend to be sort of the largest noise in our seasonal forecasts. And as I said, model deficiencies seem to limit our ability to really harvest that predictability currently. And we're looking at other issues now with how these things may be modulated by SST, by soil moisture, and global warming. So that's it. Thank you.
So if there are any questions for Siegfried, you can feel free to send him an email at his NASA email address, which you can Google to locate. And Siegfried and the next speaker, Kinsey Mo, are also co-leads on the NIDIS report on the Central United States 2012 drought. So Kinsey, are you on the line?
Yeah, I'm on the line.
Okay, great. I'm going to transfer the webinar over to your computer.
Thank you. Okay. Can you see me?
Yeah, and just go full screen, and then whenever you're ready, go ahead.
Can you see it? Okay.
Yep, looks good.
Okay. I'd like to talk about objective drought classification. As you know, with the improvement of NLDS and those models as well as the processes, we are able to select the drought events and monitor them and their development. But the thing eludes us is objective drought classification, classify drought in D1, D2, D3, D4 categories. I know the drought monitor authors has been doing that subjectively for a long time, and they did a great job, but we cannot do it somehow objectively because NLDS has very large uncertainties. We think today, because we use probabilistic approach, we are able to do something about it. That's why I like to talk to you about it. Especially, this is a time I can reach all of you, important people in the drought community, and we like to get feedback from you before we're thinking about making that into operation. Certainly, I cannot do this alone, but I don't have to because I have a privilege to working with Dr. Dennis Lantingmeyer, University of Washington. I will review current status and then talking about our approach, give an example for the 2000 to 2005 Western drought, which is one of the case study, Carestas case study. Currently, as you know, we monitor drought with three indices: SPI for precip deficit, soil moisture percentile for soil moisture deficit, and the standardized runoff index for stream flow deficit. Because soil moisture and runoff do not have long-term unified data, so we use from NLDS. And NLDS has a very large uncertainty. We'll see that in next minute. At this moment, there are two systems in operation. One is from MAGX group, Yuranxie. They are doing the NCEP system. They have 4 models, and starting 79 and in 1/8 degree. They are precip forcing. It's from CPC precip analysis. The University of Washington also have 4 models, but they are different versions, so even the name are the same. Actually, they are very different. They are much longer, from 1950 onward. And the most important thing is their data taken from the co-op stations. Those are fixed stations. So they have very large differences. You will see here for the different system, this is supposed, if everything works out, they should be very alike. They are simulating the same event. I just pick up a random one, so you don't want to say I only do it for a large drought event. This happens every month. We look at this. If you're looking at the Southwest here, you will see the EMC is much weaker, and the University of Washington is much more stronger. Even though if you look at the two patterns, they are very similar. And then also you look in the Louisiana, you will see NSAP is more severe than University of Washington. So even though the patterns are the same, they cannot do drought classification because there are large differences. In addition to the NLDS, those drought indices itself also have different time scales. I plotted here the area average for the Southeast. The red curve just low monthly mean field, no smooth. And then you can see if I plot the 6 months running mean of precip, 3 months running mean for runoff, and no smoothing for the soil moisture, apparently they are on the same time scales. Even so, if you look at it very carefully for the 2000 drought, you will see soil moisture have a little bit delay. Now the delay depends on the place, conditions, and so on. It's not regular, so I cannot use that for prediction or monitor. So, as a current status, current is that you have very large uncertainty from NLDS and also because of the indices themselves. So, status right now, we are able to select the same drought events, but uncertainty are too large. We cannot classify them. Also, the risk managers, they like to know is that they wanted to know the best and worst scenario at a given moment and their occurrence probability. So far, we are not able to give it to them. Possible solutions. There are many people have been doing this and do a fantastic job. For example, Amir talking about drought distribution. Yuan Xie reconstruct drought monitor. Both try to go away from the one indices to do the monitoring. For us, we are going to do the ensemble mean for all the indices. But if I don't do anything else, I just create another one. It doesn't help matter. We got enough indices. So we were going to do a probability approach to see how each drought category, the percentage of the indices in that category, the probability of the occurrence. We use a lot of data. We total have 18 fields, but 2 SPI, 1 from UW, 1 from CPC. Soil moisture, we have 4 from EMC and 4 from University of Washington. Also, we have 8 runoff indices. The period, because NSAP started in 79, we go from 79 to the November 2012, because this work I started in December last year, and resolution is 0.5 degree. We created grand mean indices. As you know, for example, I will use the soil as example. We have 8 models, so we can do the ensemble. And for that, we can calculate the standardized soil moisture anomaly and also soil moisture percentiles. We do that for SPI 6, soil moisture, as well as RI3. And then we just make the equal weighted mean of these 3 indices and call it the grand mean index. And we recalibrate them, make sure the grand mean index mean is 0 and standard deviation is 1, and put them in percentiles. Once it's in percentiles, we can use the classification. Drought Monitor has been using to do that in D0, D1, D2, D4. Before classification. Now let's look at what those indices look like, whether they are able to pick up the drought. Overall, I give you here is the indices for the 2000 to 2005. You will see here that drought started in 2000, and then in the 2001, you will see the intensification, Pacific Northwest, and then extended to the March. Those triangles means that state declare drought emergency at that at that given location and at that given time. And then you can see is the southwest just starting the southwest again and turn to the summer intensify. And the drought goes away, but it returned in the fall of 2003 and lasted for a couple of months. Now let's know the problem. If you're just using for each three indices alone, you will see the problem is that for the same index events, for the SPI, you will see they say, how we are in D4 already. You guys beware. But if you look at the SMP, you say, well, it's only D2 to D3. But if you look at the SRI, you'll say, what drought? It's only D1. What are you guys are so nervous about it? So this is the thing we cannot use in giving indices. And if you plot it for each individual model, you will see the same thing. Now, we use the probability approach. Now you have 18 variables. And then we can do, for each one, we can have SPI, moisture, percentiles, and so on. We have 18 indices. And then we put in the percentiles and classify them. Now, for each month and also each grid point, we just count how many indices say the drought is in the D1, D2, D3, D4 category. And then that will divide it by total number. That will be our drought occurrence. Basically, is the number of indices in that category. Now, you're just talking about drought occurrence. Of course, it will be the sum from D0 to D4. Now let's look at the Pacific event, the first one. Then you can see here is I plotted the grand mean index for the 01 and the 03 months, and here is the probability. Basically, it is saying that you have more than 60% a higher percentage Pacific Northwest is in D3, D4 category, because the D4 events not many, so I just lump them together. And so, you know, it's a very high probability. But then if you are in the inland for the Missouri Basin, Upper Missouri Basin, the drought is probably only in D0 and D1. And if you look at it here, certainly if the governor of Utah call you, you will say, what happened to my drought? I said, no, don't worry, you don't have a drought because you don't have, there's very little probability your drought will be in D3, D4 basis. But it's very possible you will have a D1 drought, and the possibility is about 20 to 40%. So you do have a drought, but not that intense. And this is discriminatory characteristic. Is also a pass for the drought monitor. Now let's look at the second case. That's intensification for the Southwest, which comes in the 2002 summer. You will see is that basically the drought from the beginning of the summer, and it can intensify from the grand mean index. Now let's look at probability of a drought occurrence. You will see again the area covered by D3, D4 in the four corner region. You can see its coverage extending, and also the percentage also increased. At the maxima, it's more or less more than 50%. But there is still have about 30%, 30 to 40% possibility in the D2. And you can see the probability for the D2 occurrence slight decrease when the D4, D3 increase. Now, in the outside region of the four corners, they do not have, you see this hole, they do not have severe drought occurrence. So if you are in California, Northern California, I say, what is my drought probability? You say, oh, you will not be as dry as those in four corners, but you do able to, you may possible to have a D1 and in the D1 category. So they also can prepare. So this will give you the probability of drought classification, how possibility will happen. So let's also look at how does it compare with the grand mean indices and also from probability. So if you have a drought grand mean in the D3 and D4 category, the probability is say most of them. If you are in the extreme, you will have a 60. More than 50% is also in the extreme category. So it does pick up that. But if you have in the D2 category, then okay, well, finish it so. Then you will see it's possible, but it's also some of them 20% in D3, D4, and also about 20 to 30% in D1, and so on and so forth. So you know the probability, the relationship between them. They do, you know, your stronger drought, you usually pick it up. So what do we learn? We learn is that grand mean index, you can capture the drought evolution, and we needed to look at this together with the probability approach to classify drought. At the extreme, they can capture drought in the D4, D3 very nicely, and one nice feature also can discriminate, and that's very useful for the water resources management. And for the Southwest case, you also see the detailed regional features, which if you just use one or two indices, you may miss that. So the advantage of the probability approach is that we can also add it as many indexes as we want to get a much more better description. And it's also taking consideration of uncertainties in the NLDAS used as our advantage. We can also give managers the best worst scenarios, and also this we can use as analyze the drought event, which I don't have time to get into. And also for those of you looking for prediction, I'm very sorry, I'm not going to get into that. I don't have time. And also for the prediction, there are difficulties how to classify those events, and also how to, how to get rid of the errors. So it's much more involved, and I'm not able to talk about that today. I do want to get feedback from you. We are thinking to make this operational because I think it will useful to the forecasters or monitoring people. But I wanted to hear from you. How do you think how we can improve, and how to have a better service for all of you? And that's it. Thanks very much to give me this opportunity.
Thanks a lot, Kinsey. And you set up the question opportunity well. So I'm going to see if I can get rid of this echo. If everybody could please check and make sure that their phones are on mute, unless you're asking a question, that would be great. Thank you.
This is Diane Cooper. Can I ask a question?
Yeah, and I think I got rid of the echo.
I put it in the chat. I didn't know if you had seen that. I'm really curious. I'm the service hydrologist in the Twin Cities, Minnesota office, to give you some background. And so we're in the middle of a drought right now. We have a situation that's ongoing where we've actually had a decent snowpack this winter. But one challenge that I'm still trying to understand from a drought monitor, drought forecast perspective is we have solidly frozen ground. So how is your model trying to account for the fact that, well, yes, we've had precipitation. We're not guaranteed right now that that water from the snowpack is going to be able to infiltrate into the ground. So it may not be a benefit from an agricultural drought. It may only help the hydrologic drought.
You ask me?
Yeah, I don't know. Does your model try to even account for frozen ground in the winter up north? Is essentially the question.
Okay, we use the NLDAS product, and they do taking into account of snow, and also snow, and they do have winter time snow, and how to monitor the snow. I think.
But that's not monitoring the frozen ground. That's just monitoring your snowpack, which is two separate
Is Mike Eck
parameters.
on the line? I think
Mike Eck is on the line.
Okay, then you can answer this better.
Yes, the physical processes of frozen soil are included.
Right.
So thermodynamics and hydraulics.
Okay, so how can you explain how that's validated?
Oh, well, we don't have ongoing validation directly. There's a number of, I guess, limited soil data sets that didn't include frozen soil. Victor Corin, the Office of Hydrological Development, had worked on that, and we put that in the model a number of years ago. And actually, I think it was data from Minnesota, frozen soils that were frozen soils in Minnesota, the data sets from there that were used to develop this. You know, certainly, always refinement is necessary. The thing is, frozen soils are not nearly as common as unfrozen soils, at least where we can actually get the data in an easier way. But so it does include the physical processes of frozen soil, and we can either directly through algorithm improvement, through the understanding of how the physics behaves and the parameters, or maybe indirectly in terms of, you know, looking at budgets and seeing, oh, what's the effect here? And well, if this was frozen, and you move a parameter a certain way, and then maybe you get a better correlation then with the resulting, you know, springtime soil temperature evolution.
Yeah, and this, just side note, if you're looking for a validation example, this year in Minnesota may be a good example because we do have solid concrete frost out there, but we have really dry soils underneath that concrete frost. So it's a very interesting dynamic going on right now.
Okay. Do you have my email? We could just start an exchange here.
I do not. I actually do have a web headline trying to explain the situation, but give me your email and I'll correspond with you.
Yeah. Oh, geez, we're talking about all this on the teleconference here.
No, that's okay.
Michael?
Yeah. So Diane Cooper and Mike Eck, you guys can maybe chat about this offline a little more.
Okay. Well, I need somebody to contact him.
Okay. Michael.eck@NOAA.gov. There you go. And we can talk about this further offline. Yes.
ECK? EC?
Oh, I'm sorry. EK.
EK. Okay. Thank you.
Okay.
Do you have any data we can use for verification in your region?
We can talk offline as to how we've been trying to handle the situation. That's probably the better way to do it.
Thank
you.
All right. Thanks. Thanks for the question, Diane. Are there any other questions for Kinsey or any of the other speakers for that matter?
Computer. I was working on a document last night.
Okay. Well, if there are no other questions, thank you to each of our speakers for this great webinar on what's going on with drought prediction. There's a lot of good work, clearly. We have another webinar coming up next month on Tuesday, April 9th on the topic of high resolution and regional modeling. And there are 5 speakers in this webinar. We're going to hear from Lucas Harris from the NOAA Geophysical Fluid Dynamics Laboratory, GFDL, Jim Kinter from the Center for Ocean, Land, Atmosphere Studies, COLA, Sarah Kapnick from Princeton University, Stefan Tulich from the Cooperative Institute for Research in Environmental Sciences, CERES, and Jiming Jin from Utah State University. So again, thanks to all of our speakers, and I hope that you'll join us again next month for this webinar on high resolution and regional modeling. Thank you.
Thanks.
Thanks, Dan, for hosting this.
My pleasure, Kinsey. Thanks for participating.
Thanks.